Welcome to Creata classes. In this lecture, we will cover Cevians. Before that, let's have a look at medians, angle bisectors and the altitudes. We have seen medians are the line segment that join the vertex with the midpoint of the opposite side. Then we have seen that angle bisectors are the line segment that bisect the angle, that is, they divide the angle into two equal parts. Then we have seen the altitudes. Altitudes are the line segment that are perpendicular to the opposite side. Now comes the Cevians. Cevians are the line segment which join the vertex with the opposite side. Just they join the vertex with the opposite side. They does not join with the midpoint of the opposite side, or they does not bisect the angle, that is, they does not divide the angle into two equal parts, neither they are perpendicular to the opposite side. Cevians are just a simple line segment that joins the vertex with the opposite side. Got it? We have done a small comparison with the other line segment inside the triangles. In this lecture, we will cover the various properties and the formulas of these Cevians. We will begin with Stewarts theorem. Stewarts theorem is somewhat similar to the Apollonius theorem that we have covered in the medians. Or you can say the Stewarts theorem in terms of medians are the Apollonius theorem that we will see just now what I am talking about. Apollonius theorem we have covered in the medians, so the proof is just similar to the Apollonius theorem. So before that, let's see what the Stewarts theorem is. For that, let's take a triangle ABC. This is a triangle ABC and AD is a Cevian. That is, AD is a line segment that is connecting the vertex with the opposite side, that is BC. D is not the midpoint, nor this line is perpendicular, nor this line is dividing the angle into two equal parts. Just AD is a simple line. Let's have the standard notation of the sides of the triangle as A, B and C. Further, let's denote the Cevian AD as X. This is X. Further, let's assume the Cevian AD is dividing the side BC into two parts, that is M and N. BD is M and DC is N. As per the Stewarts theorem, NC square plus MB square is equal to A times NM plus X square. This is the famous Stewarts theorem. As per this theorem, N times C square plus M times B square is equal to A times this complete length A times NM plus X square. Got it? You have to remember this formula. Okay? Try to correlate this formula with the figure. You will remember this. Now let's see the proof of the theorem. We can prove the Stewarts theorem through various means like the Pythagoras theorem, the cosine formula, trigonometry and other proofs also. But we will limit ourselves to the Pythagoras theorem. Let's see how we apply the Pythagoras theorem and how we get the proof of this Stewarts theorem. Let's see. For applying the Pythagoras, we should have a triangle with a 90-degree angle. But if you look into the figure, none of the angle is 90 degree. So let's draw a line which is perpendicular to BC and which is starting from the vertex A. Here this line AP is perpendicular to BC, means these angles are 90-degree angle. Let's assume PD as Y. This complete length, that is BD, is M. So we can say PB is equal to M minus Y. Got it? Here BP is M minus Y, PD is Y, DC is N and this complete length is A, that is BC. We can also write BC as M plus N. Okay, that we will see later on. After introducing this line AP which is perpendicular to BC, we got many right angle triangle in the figure. The first right angle triangle that we are seeing is APB. This is a right angle triangle. Let's apply the Pythagoras. That is, hypotenuse square is equal to the sum of square of the other legs of the triangle. We got C square, that is hypotenuse square, is equal to m minus y square plus ap square. Further, if we apply the Pythagoras in the triangle APC, we got b square is equal to n plus y whole square plus ap square. Here PC, that is this length, will be equal to n plus y. Got it? Let's move further. Let's multiply n into the first equation. Similarly, let's multiply m into the second equation. The first equation will turn out to be n3 square is equal to nm square plus ny square minus 2mny plus n times ap square. And the second equation will turn out to be mb square is equal to mn square plus my square plus 2mny plus m times ap square. We got two equations. Let's add both the equations. On adding and simplifying, we got n3 square plus mb square is equal to m plus n times nm plus y square plus ap square. Further, if you observe the triangle APD, this triangle is also a right angle triangle. So, can we apply the Pythagoras to this triangle? We got x square is equal to y square plus ap square. So, in our equation, can we replace y square plus ap square with x square? We got n3 square plus mb square is equal to m plus n times nm plus x square. Here, if you observe, m plus n is this complete length BC that we have denoted as A. So, can we replace m plus n with A? We got n3 square plus mb square is equal to A times nm plus x square. This is the proof of the Stewarts theorem. Okay, the proof is very simple. Just we have drawn the line segment AB, which is perpendicular to BC, and this line segment has created three triangles for us. And just we have applied the Pythagoras and we have got the Stewarts theorem. Further, in the starting I have told you the Stewarts theorem is linked to the Apollonius theorem that we have covered in the medians. Let's see what I mean. That is how it is linked. If we apply the Stewarts theorem to the medians, let's see what we get. We know medians are the line segment that join the vertex with the midpoint of the opposite side. If AD is a median, then D will be the midpoint. And if D is a midpoint, means both of these line segments will be equal to each other. That is BD is equal to DC, that is M is equal to N. So let's replace N with M in this equation. Here, can we replace this A with M plus N? Okay, A is M plus N and M is equal to N. On solving, we got the result as C square plus B square is equal to 2 times X square plus M square. Here we can replace M with A by 2 as M is half of the complete length A as D is the midpoint. This is the Apollonius theorem that we have covered in the medians. So we can say through the Stewarts theorem we can also derive the Apollonius theorem. Got it? So this was the Stewarts theorem and you can solve the question related to the Cevians from this theorem. Got it? Let's move to our next fundamental, that is the Siva theorem. First of all, let's see what is the Siva theorem. For that, let's take a triangle ABC with the Cevians as AD, BE and CF. Here, if you observe that these three Cevians are intersecting at a point O, means the Siva theorem will be applicable only and only when the three Cevians are congruent, that is, they are intersecting at a common point. Got it? So the formula of the Siva theorem is AF upon FB into BD upon DC into CE upon EA is equal to 1. If you observe this formula, you will observe that the line segment that we have taken are in a cyclic order, that is AF, BF, BD, DC, CE and EA. All these line segments are coming in a cyclic order. Or we can also say the product of the ratio of the segments of the Cevians in a cyclic way is always 1. Okay, multiplication of these ratios in a cyclic order is 1. So this is the famous Siva theorem. The proof is also very simple. Let's see the proof of the theorem. First of all, let's segregate the triangle BOC, this complete triangle. Further, let's assume the ratio of BD is to DC is A is to B. Okay, this is A and this is B. In the previous lecture, we have seen that if two triangles are sharing the common altitude, that is, two triangles with the same altitude, the ratio of the areas of both the triangle will be equal to ratio of their bases. Means the ratio of both of these triangles will be equal to ratio of their bases. That is, ratio of triangle BOD is to ratio of triangle COD is equal to A is to B. Why is it so? I am just repeating the fundamental, it will help you. The area of the triangle BOD is equal to half into base into height. If we take base as A and if we assume H is a height, we got the area as half into A into H. Similarly, for this triangle COD, if we take B as a base, the height for this triangle will be the same height H. Both the triangles are sharing the same height, that is H. Some may be in the doubt that the height H is coming outside the triangle. No issue, the height can come outside the triangle. Just the height or the altitude should be perpendicular to the opposite side. Here this height H is perpendicular to the line segment BC, that is BD and DC. So this height will be applicable for both the triangles. If we divide the area of the triangle BOD to the area of the triangle COD, half and H will cancel out. We will remain with A by B. That is, ratio of both the triangle is A is to B. The same fundamental we have covered in the angle bisectors. Moving further, if we take this complete triangle ABC, in the similar line, can we say the ratio of area of triangle ABD is to ratio of area of triangle ACD is also equal to A is to B? Both the triangle are also having the same altitude and the ratio of their bases will be equal to ratio of their areas. Got it? Here area of BOD upon area of COD is equal to A upon B, and also area of triangle ABD upon area of triangle ACD is equal to A upon B. If we apply the formula of ratio and proportion, can we say area of triangle ABD minus area of triangle BOD upon area of triangle ACD minus area of triangle COD is equal to A by B? Okay, we have applied the fundamentals of ratio and proportion. Let's see what fundamental we have applied. If A by B is equal to C by D, then this ratio will be equal to A minus C upon B minus D. This is the fundamental that we have used. Further, let's move to our equation. Here, can we write area of triangle ABD minus area of triangle BOD as area of this triangle, that is area of triangle ABO. Similarly, can we write area of triangle ACD minus area of triangle COD as area of triangle ACO? So, we got area of triangle ABO upon area of triangle ACO is equal to A by B. Got it? This result is very important. Sometimes the competitive exams ask such type of questions in which they give the area of these triangles and they ask for the ratio of the bases. So you should know the ratio of area of these triangles are also equal to A is to B. And here A is BD and B is DC. So we got area of triangle ABO upon area of triangle ACO is equal to BD upon DC. Moving further, similarly, we can say area of triangle AOC upon area of triangle BOC is equal to AF upon FB. Further, we can also say area of triangle CBO upon area of triangle ABO is equal to CE upon EA. The same fundamental we have used. Further, if we multiply all these three equations, we got this equation. Here if you observe, the area of these triangles will cancel out each other and we will remain with AF upon FB into BD upon DC into CE upon EA is equal to 1. That is our Siva theorem. This is the Siva theorem. Okay, the product of the ratio of the segment of the Cevians in a cyclic way is always 1. This theorem is only applicable when the three Cevians are congruent, that is, they are intersecting at a common point. Got it? Okay students, we have covered the Siva theorem and before that we have done the Stewarts theorem. Let's move to the next fundamental. For that, let's take a triangle ABC with three Cevians as AD, BE and CF. Here these three Cevians are intersecting at point O. Okay, these three Cevians are concurrent. In this fundamental, we will cover two formulas that are OD upon AD plus OE upon BE plus OF upon CF is equal to 1. And the second formula is AO upon AD plus BO upon BE plus CO upon CF is equal to 2. These are the two formulas that we will cover in this section. If you observe both of these formulas, are you able to observe here AD, BE and CF, that is the three Cevians of the triangle, are coming in the denominator of the formula? Are you able to match AD, AD, BE, BE and CF, CF? And in the first formula, OD, OE and OF is the lower part of the Cevian. Which means that if we take the Cevian as AD, okay, this is the complete Cevian AD. Here can we say AO is the upper part of the Cevian and OD is the lower part of the Cevian? Similarly, BO is the upper part and OE is the lower part of the Cevian BE. And for the Cevian CF, can we say CO is the upper part of the Cevian and OF is the lower part of the Cevian? The upper part means the part which is starting from the vertex and the lower part means the part which is touching the sides of the triangle. So in the first formula, OD, OE and OF are the lower part of the Cevian. And in the second formula, AO, BO and CO are the upper part of the Cevian. Okay, in the lower part the addition will be 1 and in the upper part the addition will be 2. You can remember like this, the upper part will be having the higher number, that is 2, and the lower part will be having the lower number, that is 1. In the first formula the addition is 1 and in the second formula the addition is 2. Got it? These are the two important formulas related to Cevians. Let's see the proof. The proof is also very interesting. Let's see what is the proof. For that, let's go back to our figure. Here, if we take the triangle BOC, this triangle, can we calculate the area of this triangle BOC? We know area of a triangle is equal to half into base into height. Here, if we take BC as a base, can we assume a line segment OQ which is perpendicular to BC? Let's denote this perpendicular line segment OQ as H1. This H1 is the altitude for the triangle OBC. Okay, that is height of the triangle. So can we say area of triangle BOC is equal to half into BC, that is base, into H1, that is height of this triangle. Further, can we calculate the area of the triangle ABC, that is this complete triangle? For that we will be needing the height of the triangle. Let's assume a line AP which is perpendicular to BC and starting from the vertex A. Let's give name to AP as H2. H2 will be the height of the triangle ABC. Now if we assume BC as a base, we can calculate the area of this triangle ABC as half into BC into H2. We got the area of both the triangles. Further, let's divide both the equations. We got area of triangle BOC upon area of triangle ABC is equal to H1 upon H2. Further, are you able to observe a triangle APD and triangle OQD? Let's take this complete section out of the figure. Here H1 and H2 are perpendicular to this line segment PD. Okay, this angle is 90 degree. Here, if we assume OQ and AP as two line segments which are intersected by the transversal PD, can we say these two angles are corresponding angles? And these two corresponding angles are 90 degree. That is, both are equal to each other. So, can we say H1 and H2 are parallel to each other? We have applied the fundamental of transversal. These two angles are equal to each other, so H1 and H2 will be parallel to each other. Got it? Here, if you observe, can we say both of these triangles are similar to each other? Angle P is equal to angle Q and angle D is common in both the triangles. So both the triangles are similar to each other. So can we say H1 upon H2 is equal to OD upon AD? Okay, we have applied the fundamental of similarities. And just now we have proved area of triangle BUC upon area of triangle ABC is equal to H1 upon H2. So let's replace H1 by H2 with our area of the triangles. We got area of triangle BUC upon area of triangle ABC is equal to OD upon AD. We got this equation. Further, in the similar way, can we prove area of triangle AOB upon area of triangle ABC is equal to OF upon CF? Okay, the same fundamental we have applied in these triangles. And also area of triangle AOC upon area of triangle ABC is equal to OE upon BE. We got three equations. Let's add all the three equations. We got this equation. Further, if you observe, area of triangle BOC plus area of triangle AOB plus area of triangle AOC is equal to area of this complete triangle ABC. Let's replace this with the area of the triangle ABC. On solving, we got OD upon AD plus OE upon BE plus OF upon CF is equal to 1. Okay, this is our first formula. Got it? Further, let's move to the second formula. Here, can we replace OD with AD minus AO? This length is OD. We can replace OD with this complete length AD minus AO. Similarly, we can rewrite OE as BE minus BO and OF as CF minus CO. On replacing and doing the simple mathematics, we got our second equation or the second formula, that is AO upon AD plus BO upon BE plus CO upon CF is equal to 2. Got it? We got the two formulas. In the first formula, OD, OE and OF are the lower part of the Cevian, and in the second formula, AO, BO and CO are the upper part of the Cevians. Okay students, we have done these formulas under the Cevians. Got it? So that's it for the Cevians. Thank you very much for being with Creata classes. Bye for now.